Now we've gone over RMS values, we can now go through power in AC circuits. Because electric power plays a central role in our systems for distributing, converting and using energy, it is a concept of utmost practical importance. When a source with an instantaneous potential difference V supplies an instantaneous current I, so it's lowercase v and lowercase I, to an AC circuit, the instantaneous power it supplies is given by P equals VI, instantaneous V times instantaneous I. First we consider power relations for individual circuit elements. If the circuit consists of pure resistance R, as in diagram A, so if we've got pure resistance here, I and V are in phase. The graph representing P is obtained by multiplying together at every instant the ordinance of the graphs of V and I. So we multiply this V with I, and you can see when you multiply, even minus times a minus gives you a plus, so you get this positive power curve above. The product VI is positive when V and I are both positive and both negative. That is, energy is supplied to the resistor at every instant for either direction of instantaneous current, although the rate at which it is supplied is not constant. Obviously it's there's some oscillations there. The power curve is symmetrical about a value equal to 1/2 of its maximum ordinate V times I, so you can see that this is the half value going through the middle here, so therefore we can just write down immediately that the average power is half VI. If we remember the RMS values for voltage and I, they are 1 over root 2 and 1 over root 2. But if you multiply 1 over root 2 times 1 over root 2, you do get half. So that's interesting, because then you can write down this average power as the root using the root mean square value. So you can write the average power is the root mean square voltage times the root mean I voltage. So I've just written that down here. So they start coming into use here now. Furthermore, since the voltage RMS equals the current RMS times R, we have that the power equals current RMS squared times R. So you can write the power like this. This equation here and this equation here have the same form as those for a DC circuit. So that's quite useful. We can now just treat this the RMS value here as thinking there they are values for a DC, so you can see they're completely equivalent. Suppose next that the circuit consists of a capacitor, as in V. So now we're going to just have an AC voltage across a capacitor. The current and voltage are then 90 degrees out of phase. When the curves of V and I are multiplied together, the product VI is negative when V and I have opposite signs. We get the power curve here, which is symmetrical about the horizontal axis. As many parts are positive as negative, and so the whole thing, the average power becomes 0. To see why this is so, recall that positive power means that energy is supplied to a device, and negative power means that energy is supplied by a device. The process we are considering is merely the charge and discharge of a capacitor. During the intervals when P is positive, energy is supplied to charge the capacitor. When P is negative, the capacitor is discharging and returns energy to the source. So no energy is actually dissipated, it's just moved around. Now in figure C, the power curve is for a pure inductor, so we got an inductor here. Now same thing for the inductor. As with a capacitor, the current and voltage are out of phase by 90 degrees, and the average power is 0 again. Energy is supplied to establish a magnetic field around the inductor and is returned to the source when the field collapses. Any combination of R, C and I, we can write this general equation down. The V, the voltage part, will have some phase angle. Then we'll have the current as cosine WT. So we allow that to either lead or lag the current here. So that equation is a general equation. The area under the positive loops is greater than under the negative loops. So you can see here there's more power in this upper section than there is down here in the lower sections. And the net average power then is positive. The preceding analysis has shown that when V and I are in phase, the average power equals a half VI. So we can see that when they're in phase, it equals a half VI, when V and I are 90 degrees out of phase, the average power is 0. So you can see when they're 90 degrees, it's 0. So you've got these in-between values now. In the general case, when V and I differ by an angle phi, the average power equals a half V multiplied by I cosine theta. I've drawn down a diagram. Basically what we're saying is there's the voltage, and we're saying that's cosine WT, yeah, the voltage. And then the part of I that's in the direction of V is what we're interested in, because that's the bit that's in phase, yeah. So that obviously is, we drop a horizontal from there to there. That's obviously I cosine the angle between them, yeah. So it's just the component of the current phasor that's in parallel with the voltage phasor there. So you can write P equals a half V I cosine phi. We can rewrite the front bit there in root mean square value, so we can write the root mean square voltage times the root mean square I times cosine the angle between them. This equation is the general expression for the power input to any AC circuit. The factor cosine phi is called the power factor of the circuit. For a pure resistance, phi equals 0 because there's no angle between them in pure resistance. The current is exactly in phase with the voltage. So in that case you'd get half VI for the resistor. For a pure resistance-less capacitor or inductor, then this angle then becomes 90. Well, if it's 90, cosine 90 is 0, so power is 0, so it works for these two here. A low power factor, large angle or lag or lead, that is normally undesirable in power circuits because for a given potential difference, a large current is needed to supply a given amount of power, resulting in large heat losses in the transmission lines. When you've got an AC source, say running a motor or something, then you want all the power delivered to the motor. You don't want any power coming back off from the inductor. You know, you don't want the inductor storing this difference and then putting it back through the connecting lines. Otherwise the connecting lines are just going to get hot and you're going to waste that energy. Many types of AC machinery draw a lagging current. The power factor can be corrected by connecting a capacitor in parallel with the load. The leading current drawn by the capacitor compensates for the lagging current in the other branch of the circuit. The capacitor itself takes no net power from the line. If we put a capacitor in line, it will balance out this angles. We don't get this waste of heat through the transmission lines. So that's a very quick intro to power in AC circuits.